In this lesson, we'll find the eigenvalues and eigenfunctions of a given boundary value problem. For basic Fourier series theory, we'll need the following three eigenvalue problems. For 4.1, we have x double prime plus lambda x equals 0, where x of a and x of b equals 0. For 4.2, we have x double prime plus lambda x equals 0, where x prime of a and x prime of b equals 0. And for 4.3, we have x double prime plus lambda x equals 0, where x of a equals x of b, and x prime of a equals x prime of b. A number lambda is called an eigenvalue of the boundary value problems 4.1 through 4.3 if and only if there exists a non-zero solution to the problem given that specific lambda. A non-zero solution is called a corresponding eigenfunction. Note the similarity to eigenvalues and eigenvectors of matrices. The similarity is not coincidental. If we think of the equations as differential operators, then we are doing the same exact thing. Think of a function x of t as a vector with infinitely many components, one for each t. Let L equal the opposite of the second-order differential operator with respect to t be the linear operator. Then the eigenvalue-eigenfunction pair should be lambda and a non-zero x such that Lx equals lambda x. In other words, we are looking for non-zero functions x satisfying certain endpoint conditions that solve the difference of L and lambda times x equals 0. Let's look at an example. We will find the eigenvalues and eigenfunctions of x double prime plus lambda x equals 0 with x of 0 equals 0 and x of pi equals 0. We have to handle the cases lambda greater than 0, lambda equals 0, and lambda less than 0 separately. First suppose that lambda is greater than 0. Then the general solution to x double prime plus lambda x equals 0 is x equals a cosine of square root lambda t plus b sine square root lambda t. This is because the characteristic equation is r squared plus lambda equals 0, where the roots are plus or minus I square root lambda. And now we consider the conditions. First we consider x of 0 equals 0, which implies a equals 0. I've shown this work on the right. If x of 0 equals 0, then we have a cosine 0 plus b sine 0 equals 0. Sine 0 is 0, cosine 0 is 1, which is why a must equal 0. And now we know x of t equals b sine square root lambda t. And now we consider the second condition of x of pi equals 0, which gives us b sine square root lambda pi equals 0. If b is 0, then x is not a non-zero solution. So to get a non-zero solution, we must have that sine of square root lambda pi equals 0. Hence, square root lambda pi, the input into the sine function, must be an integer multiple of pi, because the sine of an integer multiple of pi is equal to 0. In other words, square root lambda must equal k for a positive integer k. So if square root lambda equals k, to solve for lambda we square both sides, and we get lambda equals k squared. Hence the positive eigenvalues are k squared for all integers k greater than or equal to 1. Corresponding eigenfunctions must then be taken as x equals sine of kt, since square root lambda is equal to k. Just like eigenvectors, constant multiples of an eigenfunction are also eigenfunctions. So we only need to pick one. And now I move on to the second case, where lambda equals 0. Notice when lambda is equal to 0, the differential equation simply becomes x double prime equals 0. So we're looking for the general form of a function where the second derivative is 0, which is a linear function in the form of x equals at plus b. Notice if x equals at plus b, x prime is equal to a, x double prime is equal to 0. And now we consider our conditions. First we have x of 0 equals 0. If x of 0 equals 0, then a times 0 plus b must equal 0, and therefore b is equal to 0. Now we know x of t equals at, and if x of pi equals 0, then a times pi must equal 0, indicating a must also equal 0. This means that lambda equals 0 is not an eigenvalue. Recall from our previous notes, the number lambda is called an eigenvalue if and only if there exists a non-zero solution to one of the boundary problems listed below. And now we consider the third case where lambda is less than 0. Let's do this on the next slide. For lambda less than 0, the general solution is in the form of x equals a hyperbolic cosine of square root negative lambda t plus b hyperbolic sine of square root negative lambda t. If you're wondering where this general solution came from, recall from a previous example, if the characteristic equation has two real distinct roots, we can express the general solution as y equals c1 e to the kx plus c2 e to the negative kx. But if we use the definitions of hyperbolic cosine and hyperbolic sine, we can also express a general solution as y equals d1 hyperbolic cosine kx plus d2 hyperbolic sine kx. So going back to our problem, you now may be wondering why we have the square root of negative lambda as part of the input for the hyperbolic trig functions. Well, recall a lambda is less than 0. If we multiply both sides by -1, this is equivalent to negative lambda being greater than 0. So this is why we're using negative lambda under the square root. And now we consider our conditions. Again, first we have x of 0 equals 0, which I've shown below. Recall that hyperbolic cosine 0 is 1 and hyperbolic sine 0 is 0. So performing this substitution, hyperbolic sine 0 is 0, hyperbolic cosine 0 is 1, which indicates a must equal 0, and therefore we have x of t equals b times hyperbolic sine of square root negative lambda t. And now we consider x of pi equals 0, which indicates b equals 0. If you're wondering why b is 0, hyperbolic sine is 0 only when the input is 0, which we can verify by looking at the graph of the hyperbolic sine function, which is graphed here in red. Notice it's only equal to 0 when the input is 0. We can also see this from the definition of hyperbolic sine. We get 0 equals hyperbolic sine xi equals e to the xi minus e to the negative xi divided by 2. In order for this to be 0, e to the xi must equal e to the negative xi, which implies the exponents are equal, meaning xi equals negative xi, which is only true when xi is 0. This indicates there are no negative eigenvalues. In summary, the eigenvalues and corresponding eigenfunctions are lambda sub k equals k squared with an eigenfunction x sub k equals sine kt for all integers k greater than or equal to 1. I hope you found this helpful.